Okay, so this is the reason we're all here. Basically, as Dr. McNamara just indicated, once the uveal melanoma has spread out of the eye, almost everybody does not do well. And this picture has not changed in decades, despite throwing everything at the cancer once it's spread, including the kitchen sink, as Dr. McNamara indicated. Now, this data is from 2010, and since then, we've had the immune drugs. So probably if we were to redo this a few years from now, it is going to improve, so that's good news. But it's still not good enough, as Dr. McNamara also indicated. So that sort of picture is not true of every cancer. So there are some cancers where we have made very dramatic progress in the past few decades. In the 1970s, a child with a diagnosis of lymphoid malignancy, of a lymphoid leukemia, was not going to live. Today, almost every child with a lymphoid leukemia is going to live. That progress has come at a price, though. The treatments are very tough. And if we actually look at these children who have been cured and we follow them over decades, it's not 10% of them who have long-term side effects from the treatment. It's not 20%. It's actually 100% of them who have very significant long-term consequences of the therapy, because the treatments are pretty brutal. And coming back to the big picture, the truth is, for most cancers, it's the same story that I showed you in the first slide for uveal melanoma. If the cancer has spread, if the surgeon is unable to cut it out, so this difference between life and death is basically the difference between life and death is the surgeon. So the difference between incidence and mortality is the surgeon. If the patient comes to Dr. McNamara or myself, no matter our reasonable salaries and good quality of life, we actually don't tend to help a whole lot. And so this is the big picture. So in the whole world of cancers, there are basically only 5 cancers that doctors like Dr. McNamara and myself can routinely cure. So and they're listed here, and Dr. McNamara mentioned them. And so we really should be asking ourselves, why is it that we can't cure a uveal melanoma, but we can cure testicular cancer, even though it's spread? Why is it that we can cure pediatric leukemia, but we can't cure ovarian cancer? There has to be a reason. And for all our fancy science and genetics and blah, 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 and the trillions of dollars that get spent, surely we can do better than being so brutal. Than curing a child, but then 20 years later they have heart problems or brain problems. And so for us to answer these questions, we have to understand some really basic principles about therapy. So the first thing to understand about treating cancer, even though we use warlike terms like kill and radiate and stuff like that, it's not the same as killing a cockroach. It's not outright destruction. Cancer cells are intimately admixed with trillions of normal cells in the body, and so you can't just go and hit them like you would hit a cockroach with a slipper. Even our most warlike treatments are actually trying to talk to the cancer cell. They're trying to engage proteins and pathways as per the diagrams that Dr. McNamara showed. They're trying to talk to the cancer cell. Let me illustrate this to you with a little piece of data. So these are cancer cells from 60 patients in a test tube, and they're exposed to radiation. So they can't run, they can't hide. Every single cancer cell is being irradiated. And even then, cancer cells from some patients just don't care. If this was burning cells, it would be 0% of the cells that were surviving. It would be 0. But even though they can't run and hide, they're being radiated. Some of them are, for a lot of cancer cells from a lot of patients, they just keep on living. So the crux of the question, if we're going to answer that question, why is it that we can cure testicular cancer after it's gone to the brain and the lungs, but we can't cure ovarian cancer? We have to try and understand what is it that we're trying to, what is the pathway, what is the language that we're trying to speak to a cancer cell. So again, let's go back to basics. If we were to ask a high school student, what is cancer? They're going to tell you, it's cells that grow and divide and they don't stop. And that is exactly what it is. So what happens very often is that we all get blinded by science. We see complex diagrams with networks all over the place, but at the end of the day, this is all it is. It's cells that grow and divide and don't stop. Now, it is also important for us to recall that for cells to grow and divide is not abnormal. That's what life is. None of us would be here if cells didn't grow and divide. Right now, as I'm standing here, there are billions of cells growing and dividing in my body, in my gut, in my bone marrow, in my skin, but they stop. So really what is abnormal in cancer is not that cells are growing and dividing, but that they do not stop. And now the reasons they stop are because the main reason, the natural reason those billions of cells in my body right now are going to stop is because they achieve their specialization destiny. So the cells in my bone marrow are dividing to make white cells and red cells and platelets, and they stop when they've made a red cell or a white cell or a platelet. The cells in my skin are dividing to make skin lining, and they stop when they make the skin lining. So that's the main reason. And then there is an emergency break. If one of those cells is growing and dividing, and it acquires some damage, or it gets stressed during that process, then it will get a signal, hey, you're not behaving quite right, and so take a break and try and fix that damage. And if you can't fix that damage, then you need to commit suicide in the interest of the larger organism. So in an orderly way, you have to go away. And that's the emergency break. So how is it that cancers avoid these emergency breaks? So let's start with the emergency break. So how do cancer cells avoid those breaks? And let's start with the emergency break. So the emergency break, as I alluded to, is really a response to a range of stressors: going to the wrong place, not having enough oxygen, having damage to your instruction sheet, to your DNA. And all of those various inputs of stress, those various stressors, they converge onto a master switch called p53. Now, I want to point out that our cancer treatments, all our hundreds of cancer treatments, by and large, what they are trying to do is mimic these natural physiologic stressors. They're trying to affect the oxygen level, or the DNA, or the metabolism, the ability of that cell to make enough glucose or make enough energy. And so they're trying to create stress, and all those stressors are going to converge onto this master switch called p53, and then that p53 switch gets thrown, and then that switch will, the cell will execute those programs that I mentioned earlier. So it'll try and repair. If it can't repair, it'll execute an orderly self-destruction program. So remember, cancer cells, by definition, are wandering around, doing the wrong thing, going to the wrong place. A uveal melanoma that has metastasized has gone to the liver. It's wandered around through the bloodstream and gone to a completely foreign locale where it is going to get aberrant signals. And so for it to even execute all of that, all those very challenging actions, it cannot have an emergency brake. It has to get rid of the emergency brake. And since the various inputs converge onto a single master switch, the most efficient strategy is to interdict that core circuit, that key junction. And in fact, that's exactly what happens. So how do we know that this is exactly what happens? Because of the genomics revolution that you guys heard about earlier. So just to go back to the basics very quickly, every single cell in our body has an instruction sheet. That's the DNA that tells it what to do. That instruction sheet is organized into chapters that encode for the different proteins or mechanical components that make up our cells. So each one of those chapters in the instruction sheet of the DNA is called a gene. And the genomics revolution is basically refers to the fact that today we have the technology to get a cancer from a patient and look at that instruction sheet almost in its entirety, in a practical and affordable way. And when we do that, and we look at thousands upon thousands of cancers, we find that the most common genetic alteration, the gene that is most commonly altered in all of cancer, is in that master switch for the emergency brake, for p53. So, and other emergency brake-like genes. And why is this? So here's another implication, though, of the, before we come back to that p53 thing, here's another implication of the genomics revolution, in that we can identify because we can identify the specific genetic alterations in the cancer, like Dr. McNamara mentioned, oncogenes, etc., perhaps we can target those specific alterations. So instead of giving radiation or chemotherapy that is relatively indiscriminate in how it stresses cells, by knowing a specific altered protein, we can have a drug that just goes after that specific altered protein, so it's more selective against the cancer and not against normal cells. And that's the idea or the concept about magic bullets. And this magic bullet here is the Gleevec that Dr. McNamara talked about that we use to treat CML. So this is a great thing, and it's been a wonderful progress for some cancers, but unfortunately, the drugs that we have are actually going after this side of the spectrum, the rare genetic alterations. And in most cancers, they don't just have one genetic alteration. This story in CML, in chronic myeloid leukemia, was very spectacular because chronic myeloid leukemia is very unusual amongst cancers in having essentially just one genetic alteration. Most cancers have multiple genetic alterations, including in p53. And why is that p53 alteration such a big problem? Well, remember, our various drugs, our hundreds of agents, our chemotherapy, our radiation, they may be different. So maybe we are using idarubicin instead of cyclophosphamide, or radiation instead of etoposide, or whatever. So, so many different names, so many different drugs. But at the end of the day, if the pathway, if the brake that they are trying to use to stop that cancer cell growing is p53, and p53 is gone, you can't activate that brake if it's not there. And so we start with one drug, and hey, it doesn't work, and then we try another drug, but somehow those cancer cells, even though we're using a different drug, still don't respond. Why? Because you think you're being different, but you're not being different because you're still trying to use the same brake, the emergency brake, which is absent. And meanwhile, of course, all those stressors are going to kill normal cells where the emergency brake is intact. And so our treatments are brutal and toxic. So that basically sums up the story and the history of what we have been doing in cancer. So testicular cancer, Lance Armstrong was cured not because his doctor was a genius, but because testicular cancer is very atypical in that p53 is normal. Maybe because sperm cells are meant to wander around and they don't get stressed by doing that. So they don't need to get rid of p53. And so when we come in with our stressors, we can cure it. And all those other, except when it does have, there are rare instances where testicular cancer does have a mutation or a removal of this emergency brake. And then we can't cure it. And all those other notoriously incurable cancers like pancreatic, Steve Jobs, billions of dollars, and all these others, essentially the p53 removal rate from that cancer is 100%. And in uveal melanoma that has wandered around from the eye to the liver, it's essentially 100%. Not in p53 itself, but in cofactors for p53 that p53 needs in order to activate the emergency brake. So there has to be another way. If we are going to make progress, now the immune drugs are a different story and they are definitely progress, but if we are going to make progress with other modalities of therapy, it's not enough to say I'm going to get a new drug. The drug cannot be relying on the emergency brake. So what is the other brake? Well, there's the main brake. Why is it that we're using the emergency brake and ignoring the main brake? So first we have to understand how that main brake is activated in the first place. And we get a big clue from the Nobel Prize in 2012. Basically, this Nobel Prize went to these guys because they identified that some genes are much more important in cells than other genes. Not all genes are equal. Some genes are generals. They're not captains, they're not lieutenants, they're generals. They tell cells exactly what to do. And we even know what those genes are. And if we take those genes and we put them into any cell, we can convert that cell into any other cell in the body. So, and when we look at cancer cells, we find that the generals that they have are the generals that are trying to make what we think that cancer should have been. So in a uveal melanoma, when you look at its generals, they are the generals that would usually make a uveal melanocyte that protects the eye from the sun. So the cell embarked on the journey to become a uveal melanocyte, but never completed that journey. And now we even know why it did not complete that journey. So those generals are actually there in that uveal melanoma cell, but in order to turn on the hundreds of genes that would make an actual uveal melanocyte in the eye, it needs to use a system of on-enzymes, enzymes that turn those genes on to make the uveal melanocyte. And what happens in a uveal melanoma and in almost every cancer is that some of these on-enzymes get physically removed by those genetic alterations, by those changes in the DNA. And this shifts a dynamic balance of on and off at all of these genes towards off. So now instead of turning on those genes are turned off. The good news is that those on enzymes and off enzymes are things that we can make drugs for because they are meant to manipulate small molecules. And so we can make molecules that in turn will manipulate those enzymes. So we can actually inhibit the off enzymes using a drug and shift the balance back to on enzymes and resume that specialization destiny of the cancer cell. And if we do the same thing on a normal cell, it just does what it was going to do anyway. So a normal stem cell will make normal stem cells. We're not killing anything. We're using the main break, and we're not killing any normal cells. So this was the science, and we actually did a clinical trial. There was one drug that's actually out there already, that's an FDA-approved drug, that we could reposition or repurpose. We could use it in a way that explicitly was avoiding trying to activate emergency brakes anywhere in the body, and it was just to inhibit those off enzymes. And with federal funding, we were able to do a clinical trial, and it worked fantastic. So this was in a kind of blood cancer, and there really were no significant side effects other than related to the disease itself. And we were able to treat some of these patients with bad blood cancer, including some very old folks, for a very long time with very good benefit. And this is just one example to show you. This is an 86-year-old gentleman who had a bad form of blood cancer, and it was progressing through chemotherapy. And using this very gentle approach, we were able to extend his life for quite a few years without side effects. And, but we can't just take that drug now and use it to treat uveal melanoma or solid tumors. This drug, we could use it to treat a blood cancer because it could actually distribute into the bone marrow, but the drug itself is very rapidly destroyed by an enzyme in the body that's very highly expressed in the liver and other solid tissues of the body. So there's no way we could just do this to treat uveal melanoma, which goes to the liver. So we've improved the drug by combining it with an inhibitor of this enzyme. And again, with federal support, we were able to do clinical trials and show that the combination actually now does distribute through the liver and through the intestines. So we're actually ready now to do clinical trials in uveal melanoma and other cancers if we can get the funding. And so an obvious question is, hey, you know, why are you so clever? You know, what makes you so smart that you could do this and nobody else did? How come the trillion-dollar drug companies didn't do this? Well, because they didn't have the science. And also, it's very easy to stress cells as a concept in the test tube. It's very easy to convince yourself that you have a drug that's going to induce stress. It's much harder, it takes much more difficult science to elegantly inhibit an off enzyme without killing or stressing any cell, the cancer cell or the normal cells alone. And also another thing, another truth, another reality about the biomedical world is that it's two different worlds. There's the science world and there's the clinical world, and there's scientists who don't really understand the clinic, and there's clinicians who don't really understand the science. These guys get their money from drug companies. These guys get their money from the federal government. We only talk across the bridge of a drug company which has a completely different agenda. So progress is not necessarily as fast as it should be. The good thing about working in a place like Cleveland Clinic is we have the scientists and the clinicians all mixed up together. So this is my conclusion. Basically, our science should allow us to treat cancers in ways that are gentle and logical. And actually, we can do that, and we are seeing that. This kind of treatment that I just talked about is also a logical platform for the immune drugs, which are very exciting, because it makes a cancer show more stuff, which can then be more of a target for the immune system. And we've already proved this principle in the clinic. I don't want to oversell, but the only way for us to find out if what we're doing is going to work is we have to do the clinical trials, and we're trying to raise the funding to do the clinical trials. Thank you very much.